We will run Huffman encoding algorithm for this example. So if you see here, there are 8 characters and A is repeated 40% and H is repeated very less number of times, 2% of the time. Okay. For this problem, we'll see how to create Huffman encoding. Step number 1, create a tree for every character. So first step is create a tree for every character, 40%, and second one B 20. For C it will be 15, after that D which is 10, after that E which is 7%, after that F so which is 4%, after that G 2%, right? After that we will be having H, right? 2%. So A, B, C, D, E, F, G, H. Okay. Now what we are going to do is we are going to merge two trees out of them who have minimum frequency. What are they? G comma H. Now already I told you we can keep G here, H here, otherwise H here, G here, doesn't matter. Both will give you optimum solution. So let me merge these two. So I am creating now a new tree by merging these two. You get now 2 plus 2 4. Here you are going to get 4 as the root. Left side let's say G, right side as H, doesn't matter. Okay, here 2 and 2. Next we have 40, 20, 15, 10, 7, 4, 4. Top two minimum are this one and this one. This is F, this is G. Sorry, this one is a tree, correct? Which is neither G nor H. If I merge these two, you get what? A new node with 4 plus 4, 8. So this is a merging, right? So this is a tree now. 8 is the root. Now we have how many roots? 40, 20, 15, 10, 7, 8. Now what is the top two this time? Top two will be 7 and 8, correct? Merge them. If I merge, you get like this. E here, which is 7, and another tree I am copying here. So F here 4, and 4 is parent of son of 8. 8's right is 4, 4's left is 2, 4's right is 2, correct? And this node is G, this node is H, this node is just anonymous node. Now we are going to merge these two. If I merge these two, you get like this. 7 plus 8, 15, right? Now let me remove this one. And let me remove this one also. Now how many trees we have? 1, 2, 3, 4, 5, correct? Top two minimum. This time top two minimum will be 40, 20, 15, 10, 15. 10 and 15, correct? But which 15? We have this 15, this 15, doesn't matter. Anything you can take. So what I do is I take these two and merge, but anything you can take, not a problem. So if I merge these two, so here I am going to merge. So this will be C plus D, which is 25, correct? So this will be the new root. Now how many trees we have? 1, 2, 3, 4. Again go for merging. Which one we have to see? Top to minimum. This time minimum will be 15 and 20. Okay. So let's keep 20, which is B here. Let's merge it. So 20 plus 15, 35. This is the new root. Let's erase this one. So we have now how many keys? How many trees? 1, 2, 3. Top to minimum are this time 25 and 35. Let's merge this time this one and this one. Okay. So here let me write this tree here. 15 and 10. They are copied here. 15 plus 10, 25. Let's remove this one. I'm going to merge these two. And we know that 15 is nothing but C and 10 is nothing but D. If I merge these two, you get like this. 35 plus 55, 60. Now after that, we have now 40 and 60. Then you are going to merge these two. Then you get like this. 40 plus 60, 100. Usually sometimes what happens, people always keep smaller frequency left side, bigger frequency right side, but it's not compulsory. Okay, that is just custom, right? It's just habit. So 40 plus 60, 100. Now see character A here. So C here, D here, B here, E, F, G, H. Now we'll try to generate the code. Left side 0, right side 1. That is also convention. You can take left side 1, right side 0, not a problem. But usual convention is left side 0, right side 1. In the GATE exam, if they really ask what is the encoding of A, for that we follow the convention. Generally they should not ask like that, but if they ask, then left side character will have 0, right side character will have 1, like this. Here 0, 0, 1 here, 1 here, 1 here, 0 here, 0 here, 1 here, 0 here, 1 here, 0 here, 1 here. Now let's generate the code for A. Code for A is 0, code for B is, see, descend the tree, 1 1 0, right? Code for C 1 0 0, code for D 1 0 1, code for E here, right? 1 1 1 0. So it is 1 1 1 here 0, triple 1 0. Next F G H. What is F here, right? 1 1 1 1 0. 4 ones followed by 0. G here. So for that 1 1 1 1 1 5 1 0. H here, right? So 1 1 1 1 1 1, 6 ones. So this is about encoding, right? But you will have multiple different encodings possible, right? So, but only thing is, what is unique here is, if you use this encoding or any other encoding, which is because of the algorithm Huffman encoding, that is going to guarantee, optimum encoding. That means the message size will be reduced to optimum size. Nobody can do better than this. So this is the best compression possible with encoding schemes. Okay. Now we'll see one numerical problem related to this Huffman encoding. Example, let's say 1000 characters are given in a message. Okay, message length is 1000 characters. Then question number 1, what is the message size with respect to bits if fixed length encoding is used? Second one, what is the message size in bits when variable length encoding is used? Especially the variable length encoding is generated by Huffman encoding, we will see. So for 1000 characters, since each character in fixed length encoding, what is the size of each character? 3 bits, correct? So 3 bits and 1000 characters, it will be 3 into 1000, 3000 bits, correct? Now we'll come to variable length encoding. So it depends on frequency. 40% of the time in the message, we are going to have A that only consumes 1 bit. Then 20% of the time we are going to have B bit. So B character that will have 3 bits. Then we will have third character C, which is 50% of the time, and the length of the character C is 3. After that D. D is nothing but 3 bits and 10% of the time. So 10% of the time 3 bits plus E. What is the frequency of E? 7%. 7% of the time we will be having 4 plus this one 5 bits for F. F is 4% of the time into 5 plus G 6% of 6 bits, and G's frequency is 2%. 2% of the time 6 plus one more character is H, 2% into 6 bits. If you simplify it, what happens, we'll see. And see, into overall for how many bits? 1000. We have to multiply it by 1000. So since everywhere you will have 100 like this, all these hundreds will be cancelled with this 1000, you get 10 here, correct? So remaining thing, if you see, 40 plus 23 is a 60 plus 15 3 is a 45. It's a simplification, that's it. 10 3 is a 30 plus 7 4 is a 28 plus 4 5 is a 20 plus 2 6 is a 12 plus 2 6 is a 12 into 10. So if I simplify, it will be 40 60 100 175 195 plus 28 plus 12 40, 40 plus 12 52 into 10. So it will be 125 plus 52 will be 197, 227 into 10. It would be 227 into 10 will be 2270. Whereas this fixed length encoding requires 3000 bits. The same is 3000 minus 2270. That means almost 730 bits, correct? So for 3000 bits, 730 safe, right? So that's why definitely Huffman encoding is very important in compression algorithms. And one more thing, already I told you, Huffman encoding is the optimal solution. That means in variable compression techniques using encoding schemes, the best encoding scheme is Huffman encoding. That's why I can say this is the best compression technique we have.